Hello, here's again Stefan Möller from Hamburg, Germany. And this video blog is about a very new thing I've found here. This is this little box. This is a stump box with a tube inside. It's called the Little Beard, and it sounds like that. Yeah, so my friend Joe gave me this and he said, Steve, have a look at this nice little stump box. It's got a real tube, the 12AX7 inside, and it's got some tone pots here for a tone blend, a gain and a volume. And well, I played that and I think it's pretty great, dirty sounding little tuning thing, and I'd like to model this in my digital DSP platform, the ADAU1452 from Analog Devices, and that was a great challenge for me to do that. Actually, I thought, well, this is a little bit humming because of the plexiglass. It's not very much shielding, so I found a device from China, which is this one here, Little Beard G3. It's actually the same circuit. It's got an aluminium cabinet outside, so it's good against hum, and same pots here and the same tube. And it's got a little less drive than the original G1, but that's okay. That was already too much. I tried to contact the company and to give me the schematic to have a look at it, but they didn't give me. So I had a look and at the signal. Actually, I can show you the signal here, and it's the signal is pretty fuzzy. You see the edges at the negative signal side. That would just give this little fuzzy sound. Nice dirty thing. Pretty different to my AC30 simulation, which I loved all the years, and it's a completely different sound. I can show you here. I have a simulation of my Vox AC30 here, and it's like that. It's totally different, much smoother. You see, the signal is rounded and limited on both directions, positive and negative, and so that gives a very creamy sound. Right? Creamy, soft, not too much treble, but this little beast, a little fuzziness, which is so nice. It's actually live played through the Little Beard here, physically connected to my audio unit. Well, I thought, what's inside? What can be there? There's this tube, the 12AX7. This has usually two stages to reach the gain. They are both connected, and there may be some high pass between input and output, somewhere between. Don't know really, but I looked at the internet and searched for some other schematics of similar stump boxes with tubes inside. Actually, it's supplied with a 9-volt DC power supply, and I thought, well, maybe they have a voltage upward regulator to reach the high voltage of 140 to 200 volts at the tube to let it work in the normal constitution, but I wasn't sure, so I couldn't look at this circuit so much. It's printed circuit boards are very hard to determine what's inside. I couldn't see any integrated circuit there, so I thought, well, what's there? Okay. So I was wondering why the signal is so edgy, and then after researching the internet, I found a circuit here, which is a boost driving pedal with a 12AU7, which is a bit different, but it's similar. And you see here the two stages here. There's stage 1, there's stage 2, and input resistor and the resistors here. And you see this is connected to a battery, 9 volt. And this is very unusual for a tube to drive. And then I said to myself, well, let's start a little SPICE simulation and look how the signal and the voltages are. And I could see clearly that, it's the signal, the bias point is very high, close to the 9 volts, about 7 or 8 volts. And then you see this clipping very soon at the positive side, and it's got a long way down to the negative side. And you can see it in this signal here that it's the truth. And I can show you a bit more close. This is a sine wave. And see this? This is a little beer. And you see there's a long way down this negative signal. And if you compare it to the AC30, it's like that. You see, it's quite, there is some asymmetrically inside there, but more or less symmetrical, more or less, okay? If it's strictly symmetrical, you wouldn't have the odd and even harmonics. You would only have this and this and this and this. And but you can see the little beer has lots of harmonics here, lots of harmonics. That's why it sounds so fuzzy. I love it. Okay, stop it here. And okay. That was a good starting point for me to go to Matlab, and I built up a Simulink model. So assuming that we have nonlinearities there, it's hard to decide how much, but okay, usually 4 is enough to give the algorithm, which is the LSQ curve fit here in Matlab, which enables us to solve nonlinear curve fitting problems in a least square sense. That means you have the possibility to open this help function here in Matlab. This needs at first a X data. X data is any signal. It could be sine waves, pulses, noise, or even guitar tunes. And the Y data here is the measured signal coming from the pedal. So the distorted reference, the target, we would say. And you need the function, which is then the actual model, which I assumed here, with some blocks here like high passes inside here and there. And this is I don't use. This was for the tone blend, so I'm putting that beside. So we have 4 nonlinearities. We have some nonlinear high passes, some linear high passes here, and some linear factors, ky, ki, 1, 3, 5, and 6. Okay. Right. And to let this run, we need this function inside Matlab defined in this. The function is here, the model. It's a model function, and that describes mathematically what's been here in Simulink. Simulink is a bit easier to understand for me because it's a visualization of the model, and the actual function here is fast to calculate in the LSQ curve fit. So we have nonlinearities defined with exponential or with tangent hyperbolicus functions, and we have constant factors here for gaining. We have high passes, high pass, and nonlinear high pass function, and we have linear high pass functions. That's here. And the LSQ curve fit works so that it toggles or tries all the parameters I'm giving it, like the k factors and the nonlinearity and the nonlinear high pass function and corner frequency of the high passes, and then it puts out the result, and the result is then I use the guitar signal actually to let it optimize the parameters. And you see here there's a little tune. It's 3 seconds long from the guitar, and the black is the actual device under test, the little beer physically, and the blue one is the result of the model with the fitted parameters. And you see it's very close in every time. Okay, here and there. Okay, we can see the reaction on exponential decaying sine wave. It's 100 Hertz and 500 Hertz. You see here. Oops, very close. And here also. This is a spectrogram of 100 Hertz, the reference target and the fitted model, and the difference of the spectrogram. And this 500 Hertz. This is this time curve here, spectrogram, and the difference. And this is a guitar tune, the reference target, and the physical model. And this is the simulated model and the difference. And okay, what I want to say, I implemented this in on the DSP. There's the DSP model in SigmaStudio. So we have all the blocks here, like k factors. We have the nonlinearity, which looks quite linear. Here, hard clipping, asymmetrical, and the NL3, which is soft clipping, and the NL4 is again very hard and very asymmetrical clipping. As I told you, that the signal we find here is typical for this unit here, because of the 9 volt, the tube clips very asymmetrical, so very little positive range and long linear range, and altogether it's resulting in this function here. And yeah, let's have a listen to the model, and if it fits right. Okay, so we have again the guitar. This is the real little beer, and then we have the simulation of the little beer. Little beer again. Very close, right? And then again to the AC30. Totally different. And the little beer. Well, listen to this. This is without speaker simulation. Now we put the speaker simulation in. Okay. Much nicer, more like a real amp. AC30. Little beer. AC30. Simulation little beer. AC30. Little beer. The real little beer. Simulation little beer. Real little beer. Simulation little beer. Pretty close. Thank you for your attention.